Hello and welcome to this next session of our analytical chemistry class, where we will be discussing electrodes and sensors under the topic of electrochemistry. So we'll be finishing off on some ion selective electrodes, and we'll also be talking a little bit about pH measurements and some errors that might come into it. That'll be the first thing that we do. And later on, we might move on to topics where we can use these exclusively in our analytical chemistry for things like Redox Titrations, which will combine two topics. One, which was our titrations, which we first encountered in acids and bases. And then the second is, of course, our electrical potentials, which we have been discussing in depth here in electrochemistry. So let's get started. So errors in pH measurement, where do these typically arise from? So we found out about errors before, both systematic and random. That was way back in the early parts of this course. Now we're starting to talk about some specific errors in pH measurement. If you want to learn more about random or systematic errors, please check out those other videos. So in pH measurement, there's a couple of errors which we just cannot get rid of. That there will always be a certain uncertainty in our pH measurements. So when we report pH measurements, it's important for us to quote the limits to our measurement. So the standards here limit us to plus or minus 0.01. Whenever we're using standards, it's just kind of like it's no matter how careful we are, there's always a little bit of error associated with the use of standards. The junction potential then, so it really depends on how well we have mixed our sample. And even if we're doing like a good amount of stirring and we've equilibrated the system well, there's still a chance that the junction potential will have an effect. And that's because of the porous plug near the bottom of the electrode, which is there to sort of allow the flow of the ions through the membrane so that we can actually get a potential formed in our electrical circuit, and so we can actually get a measurement. Then that leads us to an uncertainty of around about 0.01 pH units as well. So that's plus or minus 0.01. Then again, related with this junction potential, we have a drift, which is caused by the precipitation of silver chloride or the reduction of silver plus to silver. And so we need to recalibrate every two hours. So within our pH meter, of course, we have these, the silver ions, and we also have the silver chloride solid. This can change in concentration. We can get precipitation. And so the actual physical state of our pH meter does change over time. And so it is necessary to recalibrate our pH meter. Really, it would be best to recalibrate after every measurement, but that's time consuming. So generally recalibrating every 2 hours of use is probably sufficient. And certainly every day when we start our pH measurements, we should be recalibrating before we use our pH meter, because there may have been some drift which has occurred in storage, or maybe someone else used it and they didn't calibrate it properly. You never know. It's always best just to calibrate. Then there's sodium error. So this problem arises when we have a low concentration of protons. This can be a very dilute solution of acid, or it can be due to maybe a particularly basic sample. And so this happens when the proton concentration is low and the sodium ion concentration is high. The electrode responds to the sodium ion concentration, giving a measured pH lower than the actual pH. And that's because the potential caused by the sodium ions is different from that of the protons. And remember, this pH meter is calibrated and set up to respond to the protons. And so if there aren't enough protons, then and we're measuring sodium ions, the pH meter is not smart enough to be able to tell the difference. It assumes that we're measuring protons and that we, the user, have been careful enough to make sure that we have enough protons. And then conversely, if we have too many protons, we also have a problem. So this happens in strongly acidic solutions. And so the glass ends up being saturated with protons because there just are so many of them. And this means that we get a measured pH, which is going to be higher than the actual pH. Then equilibration time. So this requires around about 30 seconds with stirring to equilibrate a solution. So this is an important thing to do whenever we're doing our measurement. We can't just put the pH meter into something and 5 seconds later get the measurement. There needs to be, if it's a solution, well, usually it's a solution, the stirring needs to be continuous, and we need to let it equilibrate for at least 30 seconds. Sometimes a little bit longer is necessary. Then the hydration of the glass. So whenever we are, usually for most pH meters, they need to be stored in a solution, a buffer solution. So the problem is that if it dries out, then we end up with not enough, like the functioning of the glass electrode is reduced, because if we recall back to the structure and the way that the glass membrane is set up, we have two layers which sandwich the dry layer of sodium in the middle, and the two on the outside are hydrated layers. So if that gets dry, then there's not enough proton ions in the sort of the first hydrated layer to actually carry any charge. And so we have to rehydrate our glass if it gets dried out. Temperature then, so changes in temperature can change the activity of the ions, and so that can cause a difference in how the system responds to our measurements. So it has to be calibrated and make sure all of the measurements are made at the same temperature. And then finally, cleaning. So we need to make sure that the electrode is cleaned properly in between measurements, so that we're not getting unnecessary drift. So the first two errors limit the accuracy of pH measurements with glass electrode to plus or minus 0.01 pH units at best. So assuming we're able to overcome the other 7 error sources, then the minimum error that we can have in our pH measurements is going to be plus or minus 0.02 pH units. So that's pretty accurate. That's reasonable enough for most uses. Like that's perfectly fine. And since there's no way to overcome those, it's the best we got. So just be aware of that there are a lot of potential pitfalls in the measurement of pH. So need to make sure that we account for them all. Okay, so ion selective electrodes. So the ones that we looked at were like the glass electrode for the pH meter. So we have glass membranes. So yeah, solid state electrodes, which we'll talk more about later, liquid-based electrodes, compound electrodes. And so the selectivity coefficient gives the relative response to a species different than the analyte, but with the same charge. So this is in instances where, for example, related to the low proton concentration error that we just saw and talked about, we can have an ion selective electrode which responds to different species of the same charge. So it could respond to sodium ions, it could respond to protons. So the selectivity of our electrode to a particular species, i.e. the one that we want versus the one that we don't want, is given here as K, which is going to have the response to X over the response to A. So if the response to each ion is Nernstian, then the relationship can be given as this. So the potential is equal to some constant related to the, what do you call this? To the system involved. Then plus or minus this term, which takes into account the concentration and the expression and the activity of a particular species. So it's 0.05916 over eta A, where we have the log then of the activity plus the sum of all of the different species which are present, which could respond to our in our ion selective electrode. So if there's more than one, like in this case of sodium and hydrogens and protons, there was only one species that we didn't want. So there's the protons, which we did want to measure, but there was also the sodium ions, which we did not want to measure. So if there were more, like maybe lithium or something like that, we would have to sum all of those up, all of their, what do you call this? All of their selectivities coefficients times their activity in the solution. And then that would give us the potential for the system. So using the selectivity coefficient, so F minus ion selective electrode has a selectivity coefficient where K, the potential K, is equal to 0.1 for the response of, because OH minus can also be, the electrode can also respond to that. So here we have a selectivity coefficient of 0.1, meaning that only about it's 10% of the response that it would have to fluoride ion. So what will be the change in electro potential when 1 times 0 times 10 to the minus 4 molar fluoride at pH 5.5 is raised to pH 10.5? And so the solution then is going to be using the equation on the previous page, where we have it here. So the potential is equal to some constant for the system plus 0.05916 divided by minus 1, which is the charge, times the log of the concentration of F minus. So that will then give us a constant where we're then multiplying by or adding a certain number of millivolts. So at pH 10.0, we can work out the OH minus concentration, which is going to be 3.2 times 10 to the minus 4 molar. How did we do that? Well, if we think back to our acids and bases work, we can relate the concentration of OH minus to the pH, because the OH is equal to 14 minus pH. So that would give us the POH concentration. Then fill that in 10 to the minus POH. So that would be what? So 14 minus 10.5 is 3.5. So then that would be 10 to the minus 3.5, which would give us this value. And so the electro potential then would be given as such. So it would be equal to E as a constant minus this value here. The reason why it's now minus is because we've divided through by this minus 1. So we just changed the sign here. That's all that happened. Times log of the concentration of the different species. So since the so 1.0 times 10 to the minus 4 plus 0.1, which is the selectivity coefficient up here, times 3.2 times 10 to the minus 4. So originally that equation that we saw on the previous slide may have looked a little bit scary, but ultimately it's really just talking about the concentrations and how much something has an effect on the overall system. So really it's not much, but it is well, it's not that it's not much. It's about what's that, about 32% of this value. So reasonable amount, I suppose. So then that will change this. So E is equal to a constant plus 229.5 millivolts. So that's changed this to this at pH 10.5. Then the change is 229.5 minus 236.6, which will be equal to minus 7.1 millivolts. And this is quite significant. Without knowledge of the pH change, you might have gotten the wrong concentration of F minus. So that's kind of how we would do those more complex calculations, where we've got to take into account competing ions. These competing ions compete with the analyte that we're interested in this case, the fluoride ion, and try to sort of complicate our results. Okay, so solid state electrodes are ion selective electrodes, and they're based on an inorganic crystal. So the fluoride electrode is given here. So we have a silver-silver chloride electrode. We have a filling solution. So we have a silver wire, and then we have silver chloride pasted over it. And then we have a filling solution here. And then we have our inorganic crystal here, which is going to be our solid state electrode. So in the fluoride electrode, it's used to monitor the fluoridation of municipal water supplies. And so this electrode is important because we don't want over fluoridation of our water, but we also don't want under fluoridation, because fluorine is an important additive to municipal water supplies. And so we employ a crystal of lanthanum fluoride doped with europium, which creates anion vacancies in the crystal. We'll talk about some of those concepts later on, but basically it means that there are holes in this membrane. Remember, ultimately these ion selective electrodes, usually if they have some sort of membrane or a crystal or they're solid state in some form, they will have some slot or some hole in the crystal structure or in the membrane structure, which will allow the ions to kind of move into that space and change the potential of the electrode and the potential of the wider system. So what we saw that in the case of the protons in the pH meter, where the protons moved into the glass electrode interface and moved into the silica glass, and that was how the potential was changed. So something similar is happening here, where the fluoride is moving into the inorganic crystal, which is the lanthanum fluoride doped with europium 2+. And so we have a filling solution here, which is 0.1 molar sodium fluoride and 0.1 molar sodium chloride. So the fluoride ions migrate across the lanthanum fluoride crystal, and that's because adjacent fluoride can jump into the vacancy, leaving behind a new vacancy. So what happens is the fluoride kind of, so say this is our interface, the fluoride can move into the, from the solution into the crystal. And then if a hole opens up, which is caused by the europium, then we end up getting a net movement of the fluoride ions. So what's happening between this picture and this picture is the fluoride ion is hopping or jumping from this space to this space, and it's leaving behind a hole. And then, so this one jumps to here. And then what can happen is that others can, because of propagating holes through the structure, the fluoride ions can actually move through the crystal by hopping from one position to the next. But there has to be a space, of course, can't jump from nowhere. So then this one could hop here. And then if there's a space over here somewhere in the extended crystal, these ones can hop through, then this one can go through, and so on. And that's how the fluorides move through the crystal. So the fluoride diffuses from one side to the other, jumping through the vacancies. And the response of the fluoride electrode is given by this, where E is equal to a constant minus beta, which is going to be some sort of electromotive constant, times 0.05916 times log of the activity of fluoride ions on the outside of the crystal. So this is going to be related to the concentration of fluoride ions in the solution. So the fluoride ion selective electrode gives a nearly Nernstian response over a fluoride concentration of around 10 to the minus 6 molar, so very dilute, to pretty concentrated 1 molar. The only interfering species then is OH minus, and at low pH, fluoride is converted to HF, to which the electrode is insensitive. So low pH is whenever we have a lot of protons in solution. Those protons react with the fluoride to produce HF, a kind of a weak acid. That's the reason why HF is formed. Normally, like for example, if it was chloride ions, they wouldn't form very easily into HCl. But because HF is a weak acid, it's possible for it to form. So yeah, the only interfering species is OH minus, assuming that it's an aqueous solution. We can have OH minus ions in solution. And so you can see here the linear response to the concentration of fluoride ions. So it goes from 10 to the minus 6 to 0. You can see that after 10 to the minus 6, it's not really linear anymore. So in very dilute solutions, it's no longer linear. And that's why it's no longer Nernstian at this range. So there should, for a Nernstian response, it should be a linear response. So even between minus 6 to minus 5, it's kind of a little bit nonlinear, but it's kind of acceptable. Acceptably nonlinear, but it's really best between 10 to the minus 5 to 1 molar. So some solid state electrodes and the ion that they measure. So here we have the different ions. We just looked at fluoride ions. We can have chloride, bromide, iodine, iodide, thiocyanate, cyanide, sulfide, and so on. And so the concentration range here is generally from very dilute up to about 1 molar. It can't really go beyond 1 molar because what happens is you tend to saturate the crystal. So the membrane potential or the membrane material is given here. So lanthanum fluoride is used for fluoride ions. Then silver compounds are generally used. Silver crystals are used for the others. pH operating ranges. So you can see that the pH at which they can be used varies. So for example, the fluoride is quite a narrow range, but this makes sense if we think about it because at high pH, we have a lot of OH minus ions, and those interfere with the fluoride. So that would change the results that we would get from our potentiometer. So that like the concentration would become hydroxide would become too much, and our data would just not really be reliable. And at low pH, we get the formation of HF hydrofluoric acid, which is a weak acid. So there's a driving force to form that, which the meter is no longer sensitive to. And so it means we're not getting an accurate measurement of our fluorine content. The others are maybe less susceptible to those things, but like for example, the chlorides, the bromides, because they're stronger acids, and so they don't really form, like for example, HCl in solution, because HCl is hydrochloric acid, which is a strong acid, and so there's no driving force there to form it. But there are quite a few interfering species, and you'll see that most of these things interfere with each other. And so it's important, it's kind of hard to it's kind of hard to measure them if there's multiple different ions present. And so we usually have to do something with our sample to remove those ions. Okay, so liquid-based ion selective electrodes. So here we have another one where we still have to have a plug. Like we can't just have the liquid and then release it into the solution. There has to be some sort of membrane, either it be a polymer or whatever it happens to be, which stops the solution in here from immediately mixing with the solution that we want to measure. We have to slow the movement of ions through the membrane. So the liquid-based electrode here has a hydrophobic membrane impregnated with an ionophore that is selective for the analyte ions. What is the ionophore? The ionophore is something which would capture or complex with the ion that we're interested in, the analyte ion. The problem is that they're not always perfectly selective towards just the thing we want. So if something else has the same charge and roughly the same size, then we're likely to get a different reading. So you have to be careful with those things. So the response of calcium 2+ ion selective electrode is given by this, where E is equal to a constant, which is a system, it's just dependent on the system of interest, plus beta, which is the electromotive force or electromotive constant. So then this is the Nernstian part here, which is related to the concentration. 2 is, of course, the number of electrons that are involved in the half reaction here. So calcium 2+ plus 2 electrons gives calcium, which is our half reaction, times the log to the base 10 of the activity of calcium 2+ outside. So really, this is related to the concentration of calcium in the solution. Strontium 2+ is the most serious interference because it's in the same group of the periodic table, and its sizes is reasonably similar. Compound electrodes then, so these make use of multiple different types of electrode and types of setups. So it could include both solid and liquid. So contain a conventional electrode surrounded by a membrane that isolates or generates the analyte to which the electrode responds. So this combination of a standard electrode, which is the inside part, and a membrane is what's going with some sort of solution inside, which will then allow us to measure the analyte. So here is the conventional electrode. Here is the membrane, which is permeable to our analyte. But unfortunately, sometimes it's hard to design an electrode which is going to be responsive to our analyte. So we might have to complex it in some way, or we might have to do another reaction in order to generate some species which we can measure. So it may be possible for the basically we're indirectly measuring our analyte. So this can be used to measure gases in solution or in the gas phase. So Spherical compound electrode for CO2 is used in the medical field to monitor patients. So what's happening here is that the CO2 diffuses through the glass, or diffuses through this this membrane here. It's just some sort of polymer. And then it enters into this solution here, which it then reacts with something inside of this solution and forms a species which can then pass through the glass electrode membrane. So it changes the concentration of protons most likely, and then those protons can move through the glass electrode into the basically a pH meter. And then since we're measuring the pH change here of this outer solution, will tell us indirectly the concentration of CO2. So some advantages of ion selective electrodes. So they're inexpensive compared to other techniques. They also tend to be faster. If you maintain it properly, it's very transferable. It's very reusable. The linear response to the log of the analyte over a wide range. So for example, there were 6 orders of magnitude for the linear response to the fluoride concentration. It's non-destructive. You just kind of put it into your sample, and then later on you can remove it from your sample and you can still use your sample for whatever you need. It's non-contaminating because usually the only ions which are diffusing in and out are the same as those already in your solution. It has a short response time. You can get a measurement within 30 seconds. Unaffected by color or turbidity. So it doesn't, it's not like, for example, UV vis measurements may be complicated if there are colored entities within the measurement. Turbidity can cause changes in the flow rate of the solution. So solid state chemical sensors. So here we're going to be looking at a little bit of semiconductors. So semiconductors can be used to measure concentrations based on electrical responses. So semiconductors and diodes. So here we just have pure silicon, where each silicon is bonded to 4 other silicons. So this silicon here is a bond to here, 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 and here. So that's just pure silicon. It is a semiconductor, but it's not a very good one. A semiconductor has electrical resistivity between that of conductors and insulators. So it's obviously not a pure conductor. It's not like some sort of piece of metal or something like that, but it's also not a pure insulator where it doesn't conduct electricity at all. And silicon is one of those things. So silicon is capable of conducting electricity, but usually we dope it with something like either reduce the number of electrons that are present or increase the number of electrons which are present. So an N-type semiconductor has an excess conduction electron. So we change the silicon for a phosphorus. So this electron is not used in the bonding, and so it's extra. And so what can happen is it can hop from the phosphorus to the silicon. So you can see here, if it hops from the phosphorus to the silicon, the phosphorus becomes positively charged because it lost an electron, and the silicon becomes negatively charged because it gains an electron. Now, if you do this over the entire structure of the semiconductor, you change its ability to respond to different potentials and different environments, and that is how we can measure samples. And then a p-type semiconductor has an excess of holes. So what does that mean? It basically means it's got electron vacancies and it can accept an electron. So here we have aluminium. We've changed one of the silicons up here for an aluminium, and then we've generated what's called a hole. The hole is just an electron vacancy. And so the holes can move through the structure by having the electrons move through it. So if the electron moves from this bond to here, it effectively breaks this bond, but it creates another hole here into which an electron can move from somewhere else. So that creates a vacancy here. Then an electron can come from somewhere else and it can fill this hole, creating a new hole somewhere else. And through the movement of these holes, we can conduct electricity. So in part A, we have the electrons of pure silicon are all involved in the sigma bonding framework. I already talked about that. So it's not true that it's not a semiconductor, but it's not a very good one. B is an impurity. Atoms such as phosphorus adds 1 electron, which is the dot, the blue dot here, which is relatively free to move through the crystal. That can be used to conduct electricity. And then down here, we've added an aluminium impurity, or we've doped it with aluminium, and this lacks 1 electron needed for the sigma bonding framework. So you see this bond is not there, but it can get an electron can jump from another covalent bond into that hole and then create a new hole somewhere else. So the hole, which is this O, blue O, is introduced by the aluminium framework and can be occupied by an electron from a neighboring bond. This effectively moves the hole to the neighboring bond. So usually in cases of semiconductors, you'll see a lot of people talking about the hole moving. Technically, the electron moves, but because the electron moves, it generates a new hole where the electron was. So it seems like the hole is also moving. And the conventional terminology and the way that these are talked about is that the hole moves. Okay, so solid state chemical sensors. So what can happen is if we have a flow of electrons, we can end up having a forward bias or a reverse bias by creating a depletion zone. So this is not so dissimilar from the junction potential that we talked about before. So a diode is a p-n junction. So that means we have an excess of holes and we have an excess of electrons. So we have here p-doped silicon and we have n-doped silicon. So we have an excess of holes here, excess of electrons here. If we have a forward bias, i.e. the negative charge here is attached to the electron-rich part and the positive is attached to the electron-poor side, we get a flow of current because the electrons flow towards the holes and the holes flow towards the electrons. If, however, we swap the electrodes around, we end up with a depletion region because the holes here move towards the negatively charged electrode with the source of electrons, and the electrons move towards the positively charged electrode here, which creates a depletion region here where there are no holes and there are no electrons, and so there is no current flowing. This is basically like a barren region of electrons. So current flows when n-type silicon is made negative with respect to p-type. This is forward bias. If the polarity is reversed, the electrons are pulled out of n silicon and holes are pulled out of p silicon, and we get a reverse bias. So a depletion layer then forms near the p-n junction here. Chemical sensing field transistors. So these are constructed of a p silicon with two n-type regions called source and drain. An insulating layer of silicon dioxide is overcoated by a metal gate between the source and the drain. So the silicon dioxide has a little bit of metal, which is of course conducting. The source and the base are held at the same potential. So the same potential is passed through them. And the drain base interface is a p-n junction in reverse bias. If the gate is made positive, electrons from the base are attracted towards the gate and form a conductive channel between the source and the drain. This is really, we will see a pictorial example of how this works shortly, which is here. So here we have the base. Here we have a metal contact. Here we have the silicon insulator, isolator, sorry. And then we have our n-type semiconductors here and here, and depending on how we pass the current through this, we will get different effects. So in this case, we have here our chemical sensing field effect transistor, and we have here a base which is filled with a p-type semiconductor. So there's an abundance of holes, but there are still some electrons, which are these blue dots. And we have two n-type semiconductors here and here. This semiconductor called the drain is held in reverse bias, which creates this depletion region here, which means that we don't actually have any flow of electrons through this. However, if the metal contact here, which is separated from the base by this insulator, if that is made positive because of some sort of chemical interaction with the metal contact, what can happen is that the positive part of this will attract these electrons towards the insulator. And if these electrons then are attracted towards the insulator, we will end up with what we'll see on the next slide, which is going to be a current flowing. So here we have it whenever we have made this metal part positive because of its interaction with some sort of chemical analyte, and then we get some sort of potential flowing. The degree to which this is made positive changes the number of electrons which are pulled towards the interface with the insulator. And so the more this is positive, the more electrons are pulled towards here, the higher and the greater the potential which will flow. And so this will then change and tell us like kind of the concentration of the analyte that we're interested in. So here's an example of a chemical sensing field effect transistor. The previous one was just kind of like a schematic drawing of the process. Here we can see what it might look like in reality. So we have here our analyte solution. We have our chemically sensitive layer. We have a protective coating over the semiconductors here and here, which are the source and the drain. And then the base and the source, of course, are held at the same potential. And the drain is held in reverse bias, so that the only way that potential can be passed through this is if we get electrons pulled towards the surface. So the operation of a chemical sensing field effect transistor is shown here. The transistor is coated with a thin insulating SiO2 layer, which is here, and the second thin layer of silicon nitride, which is impervious to ions and improves electrical stability. So that's here. And the circuit at the lower left, so this part here, adjusts the potential difference between the reference electrode and the source in response to changes in the analyte solution, such that the constant drain source current is maintained. So the changes and the response of this part is what is going to actually give us our measurement of how much a certain, a certain chemical species that we're responding to is present. So how much is there, the concentration. So, for example, silver bromide can be used as the chemically sensitive layer over the gate. Here we can see the potential changing based on the concentration of our analyte A. So the more of analyte A there is, the larger the potential of silver becomes. So when exposed to silver nitrate, silver plus is absorbed, giving the layer a positive charge. And the current increases between the source and the drain. The voltage that must be applied by an external circuit to bring the current back to its initial value is the response to silver plus. And so this then tells us, because we can then relate that response to a certain concentration, because we can see that the change in potential is related to the activity of the species, or basically the concentration of the species that is the analyte species that we're interested in. And so by relating that to a certain table of calibration that we know, then we can actually find out how much, in this case, silver there is in the silver nitrate solution. Okay, now let's have a look at our redox titrations in our electrochemistry. So this is combining the two topics that we have previously been talking about, our titrations in our analytical chemistry and our oxidation reduction as related to the electrochemistry. So let's combine them. Let's see how we can actually get nice measurements using this technique. So redox titrations are based on an oxidation reduction reaction between the analyte and the titrant. So an oxidation reduction reaction can produce an electrical potential, which we can measure. So here are some common oxidants and some common reductants. So we have chlorine, we have hypochlorite, we have atomic oxygen, ozone, hydrogen peroxide. These are all common oxidants or oxidizing agents, which are themselves reduced. And then we have some reductant, which are things like ascorbic acid, which is vitamin C. We have borohydride, we have ferrous, we have tocopherol, which is vitamin E. We have sulfur dioxide, and we have sulfite. And so these are reductants, they're reducing agents, and so they themselves will be oxidized or they will lose electrons. So here is kind of like how it goes. So we have a beaker with our analyte, we have our reference electrode, could be calomel, could even be the standard hydrogen electrode, just depends. Then we have our analysis electrode here, which is our platinum wire. It's pretty common to use platinum wire because it's not that reactive. Then we have our magnetic stirrer bar down here at the bottom, and then we have a burette containing some sort of oxidizing species. So consider the titration of iron 2 with the standard cerium 4 monitored potentiometrically with platinum and calomel electrodes. So what's going to happen is that the iron is going to deposit onto the platinum wire, and so that half reaction is going to cause the flow of electrons through the system. And the titration reaction is cerium 4 plus iron 2 plus gives cerium 3 plus plus iron 3 plus. So what's happening here is that the iron is being oxidized and the cerium is being reduced. So at the platinum indicator electrode, two reactions come to equilibrium. We have iron 3 plus plus an electron gives iron 2 plus, which has this standard potential at standard conditions of 25 degrees Celsius and 1 atmosphere. And we have a cerium being reduced. Cerium 4 plus plus electrons gives a cerium 3 plus, which has this potential here. So before region one, okay, so we still have regions. Of course, we have a titration curve, so we still have regions in our titration. So before the equivalence point, we can use either the indicator half reaction to determine the voltage. And before the equivalence point, we know that the concentration of iron, the concentration of iron 2 plus and iron 3 plus, because we know how much cerium we have added, and we know how close we are to the equivalence point based on how much we've added. So the potential then is equal to the sum of, or the difference of the positive and the negative. So the reduction and the the oxidation and the reduction. So here we have the Nernst equation for that. So this is our reference electrode, which is our standard calomel electrode here. And then we have here the term which is based on the reaction quotient of the iron 2 plus and the iron 3 plus. We have here the standard potential for that reduction. And then this is just the part which is related to the concentrations of the species present. So then we just fill in these values and we calculate it, and we get the overall potential is going to be equal to 0.526 minus 0.05916 volts times the log to the base 10 of the reaction quotient of the reduction. So before the equivalence point, the point at which the volume is equal to half of the equivalence point is analogous to the point at which the pH is equal to pKa in an acid-base titration. So E plus is equal to E, the standard potential for the iron 3 plus, iron 2 plus reduction couple. And then region 2 at the equivalence point. So this is where we've reached the equivalence point. So exactly enough cerium 4 plus has been added to react with all of the iron 3 plus. So all of the iron 3 plus has been reduced to iron 2 plus at the equivalence point. So that means that the concentration of cerium 3 plus is going to be equal to the concentration of iron 3 plus, and the concentration of cerium 4 plus is going to be equal to the concentration of iron 2 plus at the equivalence point. So at the equivalence point, both half reactions are in equilibrium with the platinum electrode at the equivalence point, and it is convenient to use both of them. So at the positive potential is equal to 0.767 minus 0.05916 times the log of the reaction quotient for the reduction. And then the potential of the reduction is equal to 1.7 times, or for the cerium half reaction. So that's going to be 1.7 minus 0.05916 times the log to the base 10 of the reduction of the cerium 4 plus to cerium 3 plus. So because the concentrations of cerium 3 plus and the concentration of iron 3 plus and the concentration of is equal to, these concentrations are equal, and these concentrations are equal, we're able to work out the cell voltage. So the cell voltage is E is equal to the potential at the reduction minus the potential at the oxidation, which is our reference electrode, is equal to 1.23 minus 0.241, which is going to give us a total potential to the cell of 0.99 volts. So after the equivalence point, so this is kind of like where we're either in the acid rich or the base rich type point, but this is not, this is based on the potential of the system. So the moles of cerium 3 plus are equal to the moles of iron 3 plus. And that doesn't change because as we keep adding more and more cerium 4 plus, we don't actually reduce it anymore. It no longer gets reduced from cerium 4 plus to cerium 3 plus. And so there's going to be an excess of unreacted cerium 4 plus. And so because we know the concentration of cerium 3 plus and the excess cerium 4 plus, it's convenient to use the half reaction here. So the potential is equal to the potential of the reduction minus the reference potential, which is equal to this, which is 1.70, the Nernst equation basically for that reduction minus the potential of the reference electrode. Okay, so this is kind of what it looks like. If you remember what a standard strong acid, strong base titration curve looked like, it might seem familiar to you. So we have the amount of added oxidizing agent, which is the cerium 4+, and we have the potential here on the y-axis, which is analogous to our pH. So we're going to do some calculations. So a volume of 100 milliliters of 0.05 molar iron 2+ is titrated with 0.1 molar cerium 4+ using the setup seen earlier. The equivalence point is when the volume of cerium 4+ is equal to 50 milliliters. Calculate the cell voltage at these volumes of added cerium 4+. So the volume equivalence volume is equal to 50 milliliters because the concentration is twice that of the iron 2+. You could do V1 times C1 is equal to V2 times C2 to get that. Okay, so let's do part A. So part A is 36 milliliters of solution added. So this is going to be 36 over 50 of the equivalence point. So it's 36. So it's about 72% of the way to the equivalence point. So that means that 36 out of 50 milliliters of iron, or sorry, a fraction, basically 72% is iron 3+, and about 28% is iron 2+. How is it 28%? How is it 72%? Just multiply by 2 and you'll get the percentage, because it's base 50 and base 50. So that means that the concentration of iron 2+ over the concentration of iron 3+, i.e. our reaction quotient, is going to be 14 over 36. And then that means that we can fill it into this equation. So we already know the standard potential for this. So the reduction potential at the reduction electrode is equal to 0.767 minus 0.05916 times log to the base 10 of 14 over 36, which is equal to 0.91 volts for the system at that concentration. And so 36 milliliters is somewhere around a bit here in our titration curve. But remember that this is only for the this curve is for the total potential of the system. We've only worked out the reduction potential. So in order to get the potential for the system, we need to subtract from this the standard reference electrode, which is going to be our calomel electrode. So here we have the potential for the system, which is the reduction potential, which we've just calculated as 0.791 here, minus the potential of the calomel electrode, which is 0.241, which is equal to 0.550 volts. Okay, then let's do it at the equivalence volume. So since cerium 4+, since the overall reaction is cerium 4+ plus iron 2+ gives cerium 3+ plus iron 3+, all ions are going to be in the form of cerium 3+ and iron 3+ at the equivalence point. Because all of it's reacted. All of the cerium is reacted with all of the iron to give these two species. So then the potential at the reduction is going to be, well, we can use either actually. So the potential at the reduction electrode in terms of iron is going to be 0.767 minus 0.05916 times log to the base 10 of the reaction quotient here. What's happening is that this is the Nernst equation for the iron, and then the Nernst equation for the cerium is the potential at the reduction electrode is equal to 1.70 minus 0.05916 log to the base 10 of the reaction quotient of cerium 3+ over cerium 4+. So that means that we now have to use both of them. So twice the reduction potential is going to be equal to 0. So basically add these two together, the one for the cerium and one for the iron. So 0.767 plus 1.70 minus this Nernst expression for the based on the concentration of the cerium ions, and this part here based on the concentration of the iron ions. So it's going to end up being like this. So we've added these two together and we've combined these two terms. So because the cerium 3+ concentration and iron 3+ concentration and the cerium 4+ and concentration is equal to the iron 2+ concentration at the equivalence point, the ratio of concentrations is unity, meaning the log term is 0. So this all becomes 0, and 2 times E plus is equal to 2.467. So that means we have to divide that by 2 to get the reduction potential, which is going to be equal to 1.23 volts. So this was, we wrote this out explicitly to show you the full process, but actually you can usually kind of, if you're at the equivalence point, skip ahead to the end, which is basically just adding the standard potentials together and dividing by 2 in a redox titration of this type. So the overall potential at that amount of cerium 4+ added is going to be equal to the potential at the reduction electrode minus the potential of the standard calomel electrode is equal to 1.23 minus 0.241 is equal to 0.99 volts. Okay, so finding the endpoint then. So a redox indicator changes colors when going from its oxidized to reduced state. So here is an example of one of those. So we have here oxidized ferroin. This is pale blue, and this is whenever the indium is oxidized. Then whenever we're the indicator is oxidized, it's pale blue. Whenever it's reduced, it's going to be red in color. This is the iron here. Whenever we reduce the iron 3 to iron 2, it goes red, goes from blue to red. So the color change will be over the range here, which is the potential is equal to the standard potential plus or minus this Nernst expression here, where N is, of course, the number of electrons in the half reaction. And so a redox indicator will give a satisfactory endpoint when the differences in the formal potential is greater or equal to 0.4 volts. So here are some redox indicators when we're finding the endpoint. So we have a phenosafranine, we have indigo tetrasulfate, we have methylene blue, we have diphenylamine, and you can see some of the color changes. So some of them go from colored to colorless. Usually when they're reduced form, they're going to be colorless. Usually they're not going to be colorless in their oxidized form. And here we can see the standard potential for each one of these indicators. Finding the endpoint then is going to be based on the changes in the potential as we add more and more of our titrant. So a grand plot then uses data from well before the equivalence point to locate the equivalence point. And data from close to the equivalence volume are not accurate because electrodes are slow to equilibrate when one member of the redox couple is nearly gone. And so that means that we need to actually extrapolate to get our equivalence volume. And so a graph of the volume times 10 to the minus n E over 0.05916, which was how we found the equilibrium constant, if we recall, versus the volume added should be a straight line with x intercept being equal to the equivalence volume. So here we have this plot here, and the x-intercept here is going to be our equivalence volume. So finding the endpoint of our reaction. So many analytical procedures are based on redox titrations of iodine. So iodine's a really good one for measuring starch content as well. So starch is the indicator of choice because the starch iodine complex is an intense blue color. Like this is really, really a strong blue color. It's very, very noticeable. So the adjustment of analyte oxidation state. So pre-oxidation, so this is a powerful oxidants that can be easily removed after pre-oxidation. Perioxy disulfate with silver plus as a catalyst. So we have excess reagent is removed by boiling the solution after oxidation of the analyte. So what we can do is we can pre-oxidize to remove things which might interfere with our titration. Silver 2 oxide, AgO, dissolves in acids to give silver 2 plus, which can be easily removed by boiling as well. So adjustment of analyte oxidation state. So sometimes we might also want to react it and remove excess solid by filtration. So solid sodium bismuthate here. So excess solid is removed by filtration. It forms precipitate. Hydrogen peroxide is a good oxidant in basic solution and can reduce chromium dichromate to chromium 3+ and permanganate to manganese 2+. It spontaneously disproportionates in boiling water, so we can just sort of boil it and we will lose the hydrogen peroxide. A disproportionation reaction is one in which a reactant oxidizes and reduces itself. So that's what happens here. So this is both simultaneously both oxidized and reduced. Another adjustment of analyte oxidation state is by pre-reduction. So this is analogous to the pre-oxidation. So stannous chloride reduces iron 3+ to iron 2+ in hot hydrochloric acid. And so excess reductant is then destroyed by adding mercury chloride. So we can react the excess reductant, the stannous chloride, with the mercury chloride to produce stannous 4+ dimercury chloride, and we can then have leftover chloride ions. So this is one of stannous chloride is a reducing agent for iron 3+ to iron 2+. We can have chromous chloride, which is sometimes used to pre-reduce the analyte to a lower oxidation state where we have excess chromium 2+ is oxidized by atmospheric O2. And then sulfur dioxide and hydrogen sulfide are mild reducing agents expelled by boiling in an acidic solution. Be careful though, because sulfur dioxide smells pretty bad. So if you're boiling this, make sure you do it in a fume hood. So adjustment of analyte oxidation state. An important pre-reduction technique uses a packed column with a solid reducing agent. So what we do is we have a solid reductant here, we pass the analyte solution through it, and so we end up with reduced analyte down here, which should hopefully be more appropriate for our titration. So we can also have things like a specific type called a Jones reductor, which is a column packed with zinc coated with a zinc amalgam, but it's not very selective. It basically just reduces everything. We can also have a Walden reductor, which is a column filled with solid silver and 1 molar hydrochloric acid, and this is more selective than the Jones reductor. Then oxidation with potassium permanganate. So potassium permanganate is a strong oxidant with an intense violet color. It is reduced to manganese 2+ in strongly acidic solutions. So it's a pretty good indicator of acidic solutions. In neutral or basic solutions, solid brown manganese oxide is the product. In strongly alkaline solutions, green manganate ion is produced. Potassium permanganate is, which is not a primary standard, is standardized by titration of sodium oxalate. So here are some of the analytical applications of permanganate titrations. We won't really go into these in much detail. It's just really for your reference. You can see it here. Oxidation with cerium 4+. So we already saw that cerium 4+ could be a pretty good oxidation agent earlier on whenever we were discussing the reduction of iron, or sorry, the oxidation, the reduction of iron 3+ to iron 2+. So cerium 4 binds anions such as perchlorate, sulfate, nitrate, and chloride. The variation of the cerium 4+, cerium 3+ formal potential is indicative of these interactions. So cerium 4+ plus an electron, so the reduction of cerium 4+ to cerium 3+ has a formal potential which changes based on the solution that it's in. And this is because of the interaction with the cerium 4 with these ions. Cerium 4+ is yellow and cerium 3+ is colorless, but the color change is not distinct. Ferroin and other phenanthroline redox indicators are well suited to titration with cerium 4+. So those are good indicators to use when we're titrating with cerium 4+. Cerium 4+ can be used in place of potassium permanganate in most procedures. Oxidation with potassium dichromate then, so this is another common oxidation agent, although all of these have been stoichiometric oxidations, meaning that it's basically 1-for-1. So it produces quite a lot of waste. But if you're doing it for small amounts, it's probably okay. So orange dichromate ion is a powerful oxidant that is reduced to chromic ion in acidic solutions. So here we have dichromate ion, we have acid, and we have the reduction using these electrons gives us iron 3+, or chromium 3+ plus water. And so it has under standard conditions, i.e. 25 degrees Celsius and 1 atmosphere, it has this potential. Dichromate is less powerful oxidizing agent than permanganate, and cerium 4+ in acidic solution. So it's a gentler oxidation agent. In basic solution, dichromate is converted into yellow chromate ion, whose oxidizing power is nil, or it doesn't oxidize at all. And so it's here. Potassium dichromate is a primary standard. Almost all chemistry labs will have this. It's very useful for oxidation titrations. The solutions of potassium dichromate are stable and pretty cheap. Oxidation with potassium dichromate. So indicators such as diphenylamine sulfonic acid or diphenyl benzidine sulfonic acid are used to find a dichromate endpoint. Reactions can be monitored with platinum and calomel electrodes. So potassium dichromate is not as strong an oxidizing agent as potassium permanganate or cerium 4+. It's used in the determination of iron 2+. So here we can see the changes that happen whenever we oxidize our diphenyl benzidine sulfonate. So it goes from this species to this species where we have, you can see a conjugated system there. So there's a change between this aromatic system and this conjugated system. So methods involving iodine. So when a reducing agent is titrated with iodine to give iodine, iodine like the molecular iodine, the method is called Iodimetry. In Iodimetry, an oxidizing analyte is added to excess iodine to produce more iodine, which is then titrated with the standard thiosulfate solution. The solubility of molecular iodine in water is enhanced by complexation with iodide. So what we have is iodine complexes with iodide to give this Tri-Iodide ion, which has quite a high equilibrium constant. So it quite easily forms this. Usually whenever we're working with iodine, we typically use starch as an indicator, as indicated earlier and talked about earlier, because it really does have a very strong color change, which is really obvious. So starch is used as an indicator for iodine, and in iodimetry titration, which is titration with this Tri-Iodide, starch is added at the beginning of the titration, and the first drop of excess I3- after the equivalence point causes the solution to turn dark blue. Like it's really incredible how dark blue it changes. In iodimetry titration of I3-, starch should not be added until right before the equivalence point, because otherwise what happens is the starch absorbs all of the I3-. So starch iodine complexes are temperature dependent. Cooling in ice water is recommended for maximum sensitivity. So the preparation and standardization of these Tri-Iodide solutions. Tri-Iodide I3- is prepared by dissolving solid iodine in excess potassium iodide. Sublimed iodine is pure enough to be a primary standard, but it evaporates while it is being weighed, so you have to be very careful and work in a cooled environment, preferably. Instead, the approximate amount is rapidly weighed, and the solution of Tri-Iodide is standardized with a pure sample of Analyte or with sodium disulfide. So acidic solutions of triiodine are unstable because of reactions. So standard triiodide can be prepared by the reverse disproportionation reaction. So iodate plus iodide plus acid gives triiodide plus water. So other methods involving iodine, so the use of sodium thiosulfate. So sodium thiosulfate is the universal titrant for triiodide. So in neutral or acidic solution, triiodide oxidizes thiosulfate or tetrathionate. So triiodide here reacts with thiosulfate to give 3 iodides plus tetrathionate here, this complex here. So we can react triiodide with this to give us iodine. In basic solution, triiodide disproportionates to iodine and HOI, so hydrogen periodate, which can oxidize the thiosulfate and sulfate ions. A stable solution of sodium thiosulfate can be prepared by dissolving the reagent in high quality freshly boiled water, so highly pure water. Dissolved CO2 makes the solution acidic and promotes the disproportionation of thiosulfate ions, so thiosulfate ion plus the acid produced from the CO2. So when CO2 dissolves in water, it produces something called carbonic acid, which is why the pH of water, which is the water we drink out of the tap or out of whatever water dispenser we have, why it doesn't have a pH of 7 because of this dissolved CO2. So it reacts according to this equilibrium. And so metal ions catalyze atmospheric oxidation of thiosulfate. So copper 2 plus thiosulfate gives copper 1 plus what was this called again? Tetrathionate. It's a pretty uncommon ion. But basically, it acts as a reducing agent, this thiosulfate. So it's added an electron here, and then it just has itself been oxidized. Then copper 2 plus half an oxygen reacts with acid to give copper 2 plus water. So it basically catalyzes that reaction. Analytical applications of iodine then. So reducing agents can be titrated directly with standard Tri-Iodide in the presence of starch. And so we can do the iodometric determination of vitamin C in a sample. So for example, if you had vitamin supplements and you were unsure of exactly how much iodine or how much vitamin C was there, were you really getting the 500 milligrams they were claiming, or were you getting less, or were you getting more? You could do an iodometric determination of vitamin C, because it will react with the ascorbic acid to form the dehydroascorbic acid plus triiodide, or sorry, plus iodide plus H plus. So oxidizing agents can be treated with excess iodine to produce triiodide, and the iodometric analysis is completed by titrating liberated triiodide with standard thiosulfate. And then we add starch right before the endpoint. Again, we don't add starch immediately because the starch would complex with the triiodide. And so that would reduce the amount of triiodide available to affect the reaction here. So finally, then we move on to some titrations of standard triiodide. So again, this is mostly just for your reference where these things can actually be used. They can be used obviously in the vitamin C, as we just saw. So the things that previously that we talked about in the slides, those are important to remember. Things here, I guess like maybe the only ones to really be like super aware of here are the fact that you can use triiodide to determine sugars in a particular sample. So like this is important for food chemistry and stuff like that. And then here's some other titrations of triiodide produced by the Analyte. So these are iodometric titrations. Okay, so that will do us for this session. Thank you for watching.